Hi, today we're going to talk about section 8.2, counting. And I know you're probably thinking this is pre-algebra. I don't need help counting. But this is, and hopefully this will be an easy lesson for you. But let's get right into it. So the book starts out, this is on page 370, it starts out immediately with an example. A guy named Kevin has a deli and he wants to have a wonderful menu, and so he's offering bread that two different kinds of bread, wheat and rye. Why rye? I don't know. It's terrible. And then meat, roast beef, turkey, and ham, and cheese, American provolone, and Munster, I think is how you pronounce that. So you can create a list. And the way you create the list is you start out with the first bread. Hang on. Start out with the first bread, which is wheat. So we put in a W for wheat. And then we go to each of the different meats. Beef. Actually, we go to the meat, and then we go to each of the different cheeses, since that's our last option. So we have American cheese. But we could also do the wheat with the beef and the provolone, or we could do the wheat with the beef and the Munster. All right, from here on out, I'm just going to say M. Then we could also do the wheat with the turkey in the American, or the wheat with the turkey in the provolone, or the wheat with the turkey in the M. Then we could also do the wheat with the ham in the American, the wheat with the ham in the provolone, the wheat with the ham in the M. Now we have exhausted all the options for wheat, but we're not done yet. We can still choose rye. Why anybody would want to, I don't know. But we have the rye with the beef in the American, the rye with the beef in the provolone, the rye with the beef in the M, the rye with the turkey in the American, the rye with the turkey in the provolone, the rye with the turkey in the M, the rye with the ham in the American, the rye with the ham in the provolone, and the rye with the ham in the M. So we get 3, 6, 9, 12, 15, 18. 18 possible choices. Good menu, Kevin. All right, so that's how you count. You can also create a tree diagram, and you do this by splitting the tree at every decision point. So I'm going to see if I can scroll it just. Let's move this up. Okay. So with the tree diagram, we have the wheat, and now we have a decision point because we could pick beef, we could pick turkey, or we could pick ham. And then when we get to that meat decision, when we decide on the meat, well, then we also have another decision point. We could do the American, the provolone, or the M. And when we get to the turkey, again, we have 3 choices. American, provolone, and M. That was really sloppy. And then for ham, again, 3 choices, and M. All right. Then we also can create the decision tree, the tree diagram for rye. Beef, turkey, and ham, but then each of these has 3. 1, 2, 3. 1, 2, 3. American provolone M. American provolone M. Sorry, getting kind of sloppy. And now my mouse is not working. There it is. American provolone M. And now we've created the tree diagrams that are described on 370. Hopefully you understand what I just did at each split, each split in the tree that shows a decision point. All right. Now let's talk about counting principle. Let me move this up. Hang on a second. Bear with me. Wasn't sure how much space I'd need for all of that stuff. All right, so counting principle. There's a fundamental counting principle. If one event has M outcomes, don't exactly know, so we're going to put in a variable M, and another event has N outcomes, then the two events together will have M times N outcomes. So Kevin has decided to shake up his world, make his deli delicious, and add a topping. He is going to allow customers to pick one of 3 toppings. They can choose lettuce, tomato, or pickles. Pickles are really good on a sandwich, so try it. But before this change, we have 2 breads, 3 meats, and 3 cheeses. So instead of counting and doing all of that and getting 18, we could have just said 2 breads times 3 meats times 3 cheeses equals 18. There will be 18 choices. Now he's going to be adding a topping, and there are 3 toppings. So now after the customer has chosen their cheese, they are not done. There's more to choose. So we will simply do 2 times 3 for the 3 meats times 3 for the cheeses times 3 for the toppings. 18 times 3 is 54. 54 outcomes. And we came to that pretty quick without having to go through all that fun counting. So now looking at this example, on page 8.2, on page 371, example 8.2a, how many possible outfits could Michelle make using 5 skirts, 6 blouses, and 4 pairs of shoes? Hopefully we're not going to be dealing with a clash between our skirts and our blouses, but that's beside the point. So we want to know the total number of outcomes. We've got 5 skirts. Keep changing it. 5 skirts, and remember you can use parentheses for multiplication. So we have 5 skirts times 6 blouses times 4 shoes, and you get 120. 5 times 6 is 30. 30 times 4 is 120. So hopefully you understand that it's very straightforward. The only other thing that we would want to ask is, if we can simply multiply the different numbers together. Why on earth would we want to ever go back to the exhaustive method? Remember this fun exhaustive list up here? Why would we go back? Why return to that when we can just go 2 times 3 times 3? And the reason is because of probability. Sometimes we need to determine how many of the possible event could occur. And so you need the exhaustive list to know how many that could be. So if we had our toppings added here, the toppings was lettuce, pickle, and I can't remember the last one. My phone's ringing, so it's got me distracted. Oh, good grief, where is it? What was the other? Oh, tomato. How could we forget tomato? Tomato is delicious on a sandwich. All right, lettuce, pickle, and tomato. So you'd have to go back, and for every decision point of cheese now, you'd have to add 3 more options: lettuce, pickle, tomato. I'm kind of combining the exhaustive list and the tree diagrams. But lettuce, pickle, tomato. Hopefully you can get a mental image of how that looks. Lettuce, pickle, tomato. Now Kevin is really into math, and he's wanting to know the probability that the next person purchasing a roast beef sandwich with provolone and lettuce on either bread type. So the important things that he's needing to know about, doesn't matter about the bread, but who is going to be getting beef and provolone and lettuce. Beef, provolone, and lettuce. Well, we would get a beef, a provolone, and a lettuce right here. So that's one possible outcome. That's where one would be. And then back over here, we would get beef, provolone, and there would be a lettuce, a pickle, and a tomato. And was it lettuce? Yeah. All right, so we would have another, we have one right there and one right there. So there are 2 possible ways that, or 2 chances that the next customer standing in line is going to ask for beef, provolone, and lettuce. Now the total number of outcomes is the 2 breads times 3 meats times 3 cheeses times 3 toppings. This equals 2 divided by 54, which equals 1 over 27. You could divide 27 into 1.00, and you would get approximately 0.37. So this is about 0.03. Oh, my mouse froze up again. Hang on. Time to reboot. What on earth? 0.37. You can multiply that by 100 to get your percent, and that equals 3.7%. So notice these little squiggly lines. It means approximate. Approximate or about. All right, that's it. Oh wait, one more example, I'm sorry. All right, example 8.2b. One second, please. Need more space. So in 8.2b, it says in 3 flips of a fair coin, what is the probability that exactly 2 flips will land heads up? So there are some key words here. The exactly 2 flips. Notice it's not at least 2 flips. It says exactly 2 flips. So that means if you get, exactly 2 flips will land heads up. Exactly 2 will land heads up. That means if you get 3 landing heads up, that doesn't fulfill the requirements of exactly 2. All right, so we're going to flip our coin. Notice we don't have anything here. We're just, the decision point is I'm going to flip a coin. And I'm going to get either heads or tails. Now, the other important piece of information is that we are going to flip the coin 3 times. 3 times. So this is time 1. Now we have a decision. We get to flip it again. And we can get heads here or tails here. That would be time 2. And here we can get heads or tails. Now time 3 we need to do because we need 3 times. All right, so we get to a decision point for head. If we got the head, we need to go a 3rd time and we could get head or tails again. Here we could get head or tails again. Here we could get head or tails again, and finally head or tails. All right, so here we've gotten heads, heads, heads. Heads, heads, heads. Here we get heads, tails, tails. I'm sorry. We need to do this again. Heads, heads, tails. So heads, heads, tails. Now we get heads, tails, heads. Heads, tails, tails. Now we get tails, heads, heads. And tails, heads, tails. And then finally, tails, tails, heads, and tails, tails, tails. And we want exactly 2 heads up. Exactly 2. What color? Pink. All right. Here we get 3. We need 2. Here we get exactly 2. Here we get exactly 2. Here we only got 1. Here we got exactly 2. Here we only got 1. Here we got only 1, and here we didn't get a single one. So the probability of, or the chances that we will get exactly 2 is 1, 2, 3. But the total number of possible outcomes is 1, 2, 3, 4, 5, 6, 7, 8. 3/8. 3/8 equals 0.375 or 37.5%. Remember, multiply by 100 to get percent. As a quick review, probabilities will always be between 0 and 1, or 0% and 100%. And the sum of all the probabilities for a particular, in a particular space, the sum will equal 1 or 100%. All right, that's it. Good luck with your homework.